Electric potentials and U. So, ladies and gentlemen, this is our next topic that comes after the idea of electric fields, electric force. We move on to the idea of what is called electric potentials. Okay, so in this, we're going to cover the ideas, again, some review of what we did last semester with potential energy, kinetic energy, and how this relates to this new stuff that we're doing with electricity, and talk about electric potential energy, electric kinetic energy, voltage, et cetera, et cetera. So I'm just going to jump to me for a couple minutes while we just talk about what the high level thing is that we're going to be doing. Right. If you remember back last semester, we learned everything in terms of vectors, culminated with Newton's laws and momentum, right? And then we paused. We said, let's go back and see if we can do all this stuff, get the same conclusions that we got before, but can we do it without vectors? Can we do it with scalars? Namely, can we do it with something that has to do with just energy? Okay, and we did that. That's when we introduced the idea of kinetic energy and potential energy. And basically, the kinetic energy, 1/2 mv squared, was studied mostly with potential energy of how high are you, right? We asked ourselves, if you have a height, do you have potential energy? The answer was yes if you have a height, no potential energy if you didn't, right? Then we had the 5-step process of using conservation of energy, kinetic plus potential equals total energy. Pick an initial spot, pick a final spot, set E initial equal to E final. That was a great procedure. People loved solving problems that way. And so, yeah, we want to use that again. So how can we do it this time? Well, if a gravitational force led to you having a gravitational potential, right? Do you have a height? Does the same thing follow for electric forces? Do you have an electric potential? That then we can just simply ask ourselves, do we have some sort of electric height, if you will, namely some R, some distance between the two from center to center? And if so, do we have a new word for that? And can we then apply that to our 5-step process? Kinetic energy is still kinetic energy, right? If you're moving, you got kinetic energy. If you're not moving, you got no kinetic energy. So that's the premise as to where we're going with this, and what and how we're going to do it. Okay, so let's jump in. That was the wrong button. Let me come up here and pause this while I get my screen shared. Okay, so let's jump right in. Let's go with our review. Or here's the topic that we're talking about today. We've already established that called potentials, right? Let's just jump back to what we know about energy from our first semester together, right? We said that there was 2 types. The first one we said was kinetic energy, which again, I remind you, is energy of motion, right? And so real easy, we ask ourselves the question, do we have kinetic energy? We're saying, are we in motion? And if we do, we have kinetic energy, which is 1/2 mv squared. Same goes no matter what type of particle, no matter what type of force, kinetic energy always has the same definition. But then we turn to this one which we established when we first brought it up, was the weird one, right? We even gave it the weird definition of potential energy. It was just energy that could potentially become kinetic. Okay, well that's great, because if it's energy that could potentially become kinetic, it's a little bit loose defined, right? What was the way that we said that chemists would like to describe this, right? This is some sort of stored energy, which makes us think of the idea of some sort of bond. And we're going to really see that come alive today, right? Last semester, we studied a particular type of potential energy that we called U sub G for gravitational potential energy, which said it was M times G times Y, which basically said if you have a height, then you have potential energy. This was a gravitational bond. It was a bond or energy stored between you, or the object, and the Earth, right? And that's how we described the idea of potential and kinetic energy last semester. Let's see how we're going to describe that in the context of what we're doing this semester, right? So remember from our last lecture, right, we now have this idea of electric force, right, which was K, Q1, Q2 over R squared, right? And then we introduced this second concept called the electric field, which was just K, Q over R squared. And how did we basically define these in the last video, right? We said this was a two-player system, right? Force between two objects, you have a two-player system. What field does one of those put out such that if you brought another one close to it, potentially, that's how we define electric field, one-player system, okay? So it's going to make sense for us then to talk about two different versions of the idea of a potential, one for the two-player system, one for the one-player system, okay? So let's start with the two-player system one, right? The one that makes sense that there should be potential energy between two charges, right? Because if you have a charge Q1 here and a charge Q2 here, and they're separated by some distance that we call R12 from center to center, well, if there's an electric force between them, well, we know it's defined by this equation up here. No problem, two-player system. But let's think about this, right? This force has units of newtons, right? So if we think about the relationship between force and energy, right? Well, we remember also from last semester that if we were to do work to this system, right? If we took one of these forces maybe and moved it towards the other one, we would all agree, whether they're repelling or attracting, we should all agree that you'd have to do work to the system. Okay, so if you believe me on that and you have to do work to the system, I remind you that work is some force multiplied by the distance, right? So what force would we be overcoming here? We'd be overcoming the electric force, and we'd be moving it a distance d. Oh, great. If we moved it a distance d, do we all agree then if I draw this in red, Q2 would now be over here, and now we would have a new red defined distance from one to the other. Cool, no problem, right? But what's the big deal there, right? Remember this thing that we did last semester called the work energy theorem, which we said that work was equal to the negative change in potential energy. So clearly, if we want to do work to the system, that's the same as saying that we can change the potential energy and vice versa. Unit-wise, right? Unit-wise, we know that work has units of energy. What are the units of energy? I remind us they are joules, right? 1 capital J, which is 1 Newton meter. A force times a distance tells us exactly how the formula then for potential energy between two particles is going to be if they're both charged. Here it is. The two-player system, namely the electric potential energy, is the electric force multiplied by its distance. Namely, if we're multiplying distance and we have square of distance in the denominator, we just get left with 1. So the potential energy between two charges is simply K, Q1, Q2 over R. And I'm just going to just erase this ever so slightly, because now remember, we don't have to obey our weird rules anymore. We don't have to obey our weird rules anymore, where again, this is just the distance between 1 and 2, where opposites attract and like charges repel, because this is not a vector. This is a potential energy. It's a scalar. It's just a number. It can still be positive or negative, right? You can still put work into the system or expend energy. So it can still be positive or negative, but now we just let the signs dictate. We use the signs. Notice there is no absolute value sign here. So this is the one major difference between it and its analog of force, okay? So if we think about two charges, Q1 and Q2, separated by some distance, is there some bond between the two of them? Is there some potential energy stored? Yes. How much? The answer is this much. And so we see, again, since this has both a charge Q1 and a Q2, we see again then that this is definitely a two-player system. And it's the word that we're used to, right? It's potential energy. It has units of joules. Okay, but there's got to be an analog for this thing called the electric field, which is the one-player system, right? The electric field, let me do this in a different color. The electric field, we remember, was related to the force by just being the electric force divided by a charge, right? So if I then ask myself the question, what is the electric potential energy divided by a charge? It wouldn't be a bond anymore, but kind of just like how the electric field was the one-player system saying that here I am, right? And I put out this field such that if you came along and landed here, this would be the force between us. We have another word to describe this, the one-player system, that says, I'm going to put out a potential, not potential energy, just a potential, such that if you landed another charge here at some distance away, we now have a potential energy bond of U. So the analog to this electric field, which was just the force divided by charge, if we then just take the potential energy and divide it by one of the charges, we get a new quantity that we're going to call capital V. KQ over R, excuse me, over just R. This is what is called not potential energy, but just electric potential. Okay, just electric potential. And so it will have the symbol capital V with those little hats up there. Okay, and what are its units? Its units is a joule per coulomb, which those of you in the class who have ever worked with anything electronic in your life, you recognize a joule per coulomb. How, at what rate are you changing energy with respect to a charge? This is also known as 1 volt, which is why another word for electric potential becomes the voltage of an object, which, yeah, that's a word that we use in our everyday language, right? It's the potential that you can, if you plug something in, this is the voltage it will give you. Right now, a 9-volt battery just sitting there outside of a smoke detector, it ain't doing nothing. It has some potential. It has potential energy inside. When you then plug it in, it then releases its potential. It makes energy become kinetic. It releases its voltage. 9-volt battery has some voltage, some potential it can give. So another way of saying that, obviously, then, is that if, let's just get the analog down here, if potential energy is KQ1, Q2 over R12, then the potential is just K, the individual charge, because remember it's a one-player system, divided by R. Again, we keep the sign, right? This could be positive or negative. And what do we then see? For our one-player and two-player system, in terms of the vector version, force and field, we have the the analog of the scalar system, which is potential energy, K, Q1, Q2 over R, and electric potential is equal to K, Q over R. Force is to force is to potential energy as field is to potential. Force and potential energy are each two-player systems. Electric field and potential are each one-player systems. Okay, that's great. That's the setup. What's the link? Again, how do we go up and down? How do we go down this chain? We go from field to force, or vice versa, by saying electric field. Wow, I really want to use that yellow, and it just really just does not come out very well. I'm gonna have to change like the color on that. How do we link these together? Electric field is just force divided by charge. Another way of saying that is force is equal to charge times electric field. Therefore, that same exact thing happens over here. Potential, like we said, is potential energy divided by charge, or potential energy is charge times voltage. Now, again, for those of you who have ever played with electronics in your life, you actually already know this, right? Because potential energy, right? Potential energy, sometimes instead of using joules as typical potential energy, sometimes people will use another type of unit called the electron volt. Notice that word there, electron volt. Volt is a unit of potential, and electron is a charge. Charge times a voltage, yes? So literally an electron volt is one of the few times in physics where this unit means exactly what it says. That 1 electron volt is equal to 1 times the charge of an electron amount of volts. So we know what the charge of an electron is, right? 1.6 times 10 to the yada, 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 okay? So if we know the charge of the electron, we can always convert that, an electron volt into coulomb, into joules and vice versa, okay? So again, joules is a measure of potential energy, which means that electron volts, even though it has that word volts in there, it still has the word electron, that's still then a measure of potential energy. Okay, good. The weird thing, again, you're going to see that this is not hard. The real thing that we have to wrap our heads around in this thing, in this chapter, is the differentiation between the two things: potential and potential energy. If we wrap our heads around the fact that there's two of them and there are two different things, we'll see that this is not so bad. And the 5-step process applies. Let's see. I want to try this problem, even though this is new, right? Let's read it together. A proton moves through an electric potential, not potential energy, but through an electric potential created by a number of source charges. So who cares how it's created, right? Its speed at a point is something at a point where its potential is 1500 V. V is volts. So right away we're saying this is potential, not potential energy. But remember, potential is related to potential energy. What will be the proton speed a short time later when it reaches a point where the potential is negative 500 volts? This is great. This problem has already explained to us that we have an initial place and a final place. It sounds like a perfect candidate for the 5-step process of energy. So let's do it. Let's pick the initial place. Oh, I'm going to zoom in a bit here. That way I can have better handwriting. I'm going to pick the initial place to be, wow, that problem really got big, didn't it? Right? When the initial potential is 1500 volts. Okay? The initial speed, and this is weird, I'll always try to put the hats on the potential, that way we don't confuse it with velocity v, is 2.5 times 10 to the 5th meters per second. And notice that they said this is a proton, which means that if it's a proton, we know the mass of the proton, and we also know the charge of the proton, right? It's just 1 times the charge of the electron, positive. Okay? We can pick the final place to be when the potential is now negative 500 volts. And when the speed is, well, we don't know. That's what we want to find out. But again, when it gets there, conservation of mass, it's still a proton. When it gets there, conservation of charge, it's still a proton. Cool, cool. Doesn't this sound a lot like our 5-step process for energy? Pick an initial place, pick a final place. So at our initial place, are we moving? Do we have velocity? Yes. How much? 2.5 times 10 to the 5th meters per second. So do we have a kinetic energy initial? Yes. 1/2 mv initial squared. What v are we plugging in for that? The velocity v, 2.5 times 10 to the 5th, not the voltage. At our initial place, do we have some potential energy stored? Well, we do. Because we have a potential. And we know that potential energy at the initial place is related to potential by being the charge of the object that we're looking at, which is a proton, times the potential initial. Conservation of energy says E initial then is add K initial plus U initial. This is 1/2 and mass of the proton, V initial squared, plus charge of the proton, potential initial. Put a check mark next to everything we know. Great. In the final case, are we moving? Yeah, we just don't know how fast. That's why we want to find V final. So do we have kinetic energy? Yes. How much of it? 1/2 mv final squared. Do we have potential energy at the final place? Yeah, it's what caused the work. It's what caused the change in motion here. Why do we know that we have potential energy in the final place? Because we have a potential. Because we have a charge, which is still a proton, multiplied by the potential at that point. E final then is 1/2 mv final squared, and that's still the mass of the proton, plus the charge of the proton, potential final. Set E initial equal to E final because energy can neither be created nor destroyed. Let's do it. That gives us the formula, 1/2 mass of proton, V initial squared, plus Q of proton, V initial potential, is equal to 1/2 mass of proton, V final squared, plus charge of proton, potential final. Put a check mark next to what we know and underline what we don't. We know. We know. One equation, one unknown. Now we're going to blast away in good old algebra fashion and solve that for V final. Final speed, not final potential. Let's do it. We subtract this whole term from both sides, and we get left with 1/2 mass of proton, V initial squared, plus Q proton, potential initial, minus Q proton, potential final. And we're going to clean that up in a second. 1/2 mass of proton, V final squared. Be very careful with your algebra here. We're now going to multiply both sides by 2 and divide by mass of the proton. So that will then tell us that we get V initial squared, speed initial squared, plus 2 mass of the proton. I'm sorry, I lied. Let's undo that. 2 times charge of the proton divided by mass of the proton times potential initial, minus 2 charge of the proton divided by mass of the proton, potential final, is equal to V final squared, velocity final squared. Now let's take the square root of both sides, which brings us to this formula here. Let's clean up this term in the middle here to make it look like last semester, shall we? We see then that this can be written as the square root of V initial squared plus 2 times the charge of the proton divided by the mass of the proton, and we're going to factor out a V initial minus V final is equal to the final speed. What does that make us think of last semester when we did roller coaster problems? Remember what the final velocity formula always looked like? It was always V initial squared plus 2G Y initial minus Y final. Take a look at the form of this. Speed initial squared plus some constant, change in potential. Speed squared, some constant, change in height. Same exact procedure if we review this as we did last semester, just with this new verbiage again of potential versus potential energy. We will do more problems like this as the week goes on, but I want you to take a day or two to digest this, get used to the difference in verbiage, and realize that, yeah, potential energy we think of as bonds. Potential, though, is a voltage. It's the thing that we talk about when we're talking about batteries that we put in all different types of objects. Okay, let's see if we can make this come back. So that's it for today in terms of this. The next video will consist of us doing just lots more problems with potentials and potential energy. And then like we had in the previous video, we're gonna have to add in the idea of continuous media, rigid bodies, and how it affects the idea of potential versus potential energy. Ladies and gentlemen, please make sure that you take a look at this. I hope that you're staying safe and well, and I look forward to seeing you in our next installment. Have a great night.